Multivariable Calculus, Section 11.7, Cylinders and Quadratic Surfaces. Okay, we're going to start with some notation. What f of x comma y equals 0 means is that we have an expression in x and y equal to 0. Not necessarily a function, it could be a relation. For example, x squared minus y squared minus 25 equals 0 in 2 dimensions, because we have 2 variables, is in fact the red hyperbola shown at the right. Now, the f of x y equals 0 is usually a curve in 2 dimensions with some exceptions. For example, if we have x squared plus y squared equals 0, x and y both have to be 0, and so all we get is a point at the origin, not a curve. Now, if we have 3 variables, f of x comma y comma z equals 0 means that you have an expression in x, y, and z set equal to 0. For example, x squared plus y squared plus z squared minus 100 equals 0 is the equation for a sphere of radius 10 centered at the origin. Now, usually f of x comma y comma z is a surface with some exceptions. For example, if we have x squared plus y squared equals 0 in 3 dimensions, that means x and y still have to both be 0, but z can be anything, and so the graph of that would be the z-axis, namely a line, not a surface. Traces. A trace is the intersection of a plane with a surface. So here's a picture of a sphere, which is a surface, and then the plane cuts through the sphere, and the trace then is a circle. Here is just a bunch of traces that, if you had infinitely many of them, would make up a sphere of radius 5. Cylinders. Let C be a curve in a plane, and L a line not parallel to that plane. So you could have a circle, and then the red given line, or you could just have any kind of squiggly curve. A cylinder is a set of all lines parallel to L that intersect the curve. So this is what the cylinders would look like. Now, on the left, we have a right circular cylinder, the one that most people think of when you think of a cylinder, except notice that in math class, the cylinder doesn't stop. It goes up forever and down forever. And then on the right, we just have a peculiar looking screen looking thing that is also considered a mathematical cylinder. The curve is called the generator, and the lines are called rulings. So here we have a circularly based cylinder, but the lines are not perpendicular to the plane. They don't have to be perpendicular. This is called an oblique circular cylinder. And in fact, even a plane is a cylinder of sorts, because you can use the line as the blue line as the generator, and then the red lines, the rulings, form a plane that intersects the green plane that the line is in. Quadratic surfaces. Quadratic surfaces always have an equation of this form. A, B, C, D, E, F, and H are real numbers, and they cannot all be 0 in order to get a surface. Notice there's no xy, xz, yz, or xyz terms. If you put those in, then it gets more complicated, and it's no longer considered a simple quadratic surface. There are some special quadratic surfaces that we're going to study and draw. We have an ellipsoid. Notice that the equation looks very similar to the equation for an ellipse in 2 dimensions. We have elliptical paraboloids. So the cross sections, some of the cross sections are parabolas, and some of the cross sections are ellipses. We have an elliptical cone. Now, notice that the x comes first and that the z comes last, and when the z comes last on the right side, then your cones will be centered on that z-axis. If you switch the x, y's, and z's, then you get cones centered on different axes. Now we have a hyperboloid of one sheet. Here's what it looks like. It's one surface. Now the picture below is wrapping around the z-axis, and that actually matches the large equation above it. Notice that we're subtracting z squared over c squared. Then we have a hyperboloid of 2 sheets. Now notice the little tiny equation down there by the picture starts with z squared over c squared, and this one has to start with the axis that it's wrapping around. So if we use the larger equation with the x squared first, then these two surfaces would be sitting on the x-axis, not the z-axis. And we have a hyperbolic paraboloid. And the reason it's called a hyperbolic paraboloid is if you look at traces going one way, they're parabolas, but if you look at them going the other way, they're hyperbolas. So notice the little tiny equation again starts with y squared, and that's because this particular sketch, the surface is sitting on the y-axis, kind of going over, the parabolas are going over the y-axis or going along the y-axis. If we use the larger equation that starts with the x squared, then the parabolas would be running along the x-axis, not the y-axis. Now, hyperbolic paraboloids look like something you've probably eaten at some point in your life. Can you guess what? Pringles. Pringles are in the shape of hyperbolic paraboloids. Yummy. Surfaces of revolution. Okay, back in 2 dimensions, we used to take a curve and swing it around an axis and cause a surface that has circular cross sections. Now, the book uses the same x, y, or z, whichever they're using for the curve, as they use for the surface. And to me, that's confusing because they're not the same. So I'm going to use a subscript for the curve. Here we have z1 equals y1 squared for the curve. But you can see that in the circle, those green radii, as the green radii moves around, on the surface, the z and the x vary. They're not always the same as the ones on the curve. And so I'm going to use x and z for those. Now, y, on the other hand, is always the same as y1. Notice that the radius is always equal to the z value on the curve, which is z1. And then on the circle, your x squared and your z squared are, when you add those together, you get the radius squared because those are circles with radius z1. And the y value for the 3-dimensional y is always going to be the same as the y value on the 2-dimensional curve. So y is equal to y1. Now what we're going to do is we're going to combine these, and we're going to be replacing y1 with a y. And so we have z1, for example, equal y1 squared, which is equivalent to y squared, because y and y1 are the same. And that leads us, if we square both sides, to the fact that z1 squared equals y to the 4th. Well, why do I need that? Well, in that third equation, I have a z1 squared. So now I'm going to take this equation, and I'm going to replace z1 squared with its equivalent, namely y to the 4th. And so this is an equation for the surface in x, y, and z in 3 dimensions. And if we want to rewrite that equal to 0, then we would just bring the y to the 4th over. Now, meanwhile, I'm going to check some points to make sure this makes sense. Here's an obvious point. 9, 4x means that y has to be 3, and z is 0. Because we're not moving up or down. That radius is coming straight out towards you. Do those numbers satisfy the equation? Yes, they do. Let's try another point that's not quite so obvious. That one is 7 along the x-axis, 3 along the y-axis, of course, and then up 4 root 2. Put those numbers in, and we have 49 plus 32 equal to 81. And so that also works. Okay, this is number 2, and this is the surface that they want us to draw. Notice that z is not here, so that means z can be anything. So when z is 0, we get this line in the xy plane. And when x is also 0, y would be 15. So let's call this 15. Let's call that 15. And then when y is 0, x would be 10. So let's just call this 10. So that means that we have a line in the xy plane. And the part that we see in the first octant is this part right here. So I'm going to make that blue. Now, since z can be anything, that means that z can go up and down anywhere from these lines. And so what the book is calling rulings, yeah, that's it, are these lines going up and down. This is actually a cylinder where the curve is a straight line. And then so we can make this look like a plane. Of course, it continues on out. And so this is a cylinder whose rulings are lines parallel to the z-axis. And the curve generating it is the line 3x plus 2y equals 30 in the xy plane. Sort of a flat cylinder. Okay, this is number 8, and we're starting again with a curve that we can draw in the xy plane when z is 0, but then z is going to be able to be anything up and down. So I'm going to rewrite this in a way we'll recognize it by dividing by 36. Oops. So we recognize that as an ellipse, so I'm going to draw that ellipse in this plane. So on the x-axis, I want to go 3, so let's call that 3, and that -3, only that really should be smaller to be in perspective. And then on the y-axis, 2. Let's make 2 a little bit bigger. Let's call that 2, and that -2. And so we have an ellipse, which is a little bit hard to draw in perspective, but you kind of get the idea. And then z can be anything, so z is going to go up and down from that. Within that curve is going to move up and down the z-axis and create an ellipsoid-based cylinder. I mean, you can try to make it look more. We should dot this because this is like behind the y-axis, and so this part is showing. So something like that. So again, this is a cylinder with an elliptical base and rulings, again, parallel to the z-axis. And if I were going to hand this in for a grade, I would pretty it up a little bit. You know, draw it nice. So here's number 26 from the text. We've got x squared minus y squared minus 9z squared equals 9. Now if I look at my handy dandy quadratic surfaces chart here, I'll notice that this is the equation we're looking at. The quantity squared and then minus the other two squared quantities equals 1. Of course, we haven't got it in that form, but that shows you that it's going to be a hyperboloid of 2 sheets. Now, on this example, the z squared comes first, and therefore your 2 surfaces are on the z-axis. So in our case, our 2 surfaces are going to be on the x-axis. So if I make the x-axis come out this way, as I usually do, that's going to make drawing it very difficult, drawing hyperbolas on the x-axis when half of them are back here. So instead, I'm going to call this the x and y-axis and have the z-axis poking out towards you, and that's going to make the drawing a lot easier. Okay, so the first trace I want to look at is z equals 0. When z is equal to 0, we get x squared minus y squared equals 9. And in pre-calculus class, we usually write it like this. And that's a hyperbola. And to draw that, the way I used to teach my pre-calc classes is we go, this is a squared and this is b squared, which are both the same. So it's a square hyperbola. So we go 3 units on the x, 3 units on the y, and make a little box. And if that were a plus sign in between the two terms on the left, it would be an ellipse, and it would be a whole lot easier to draw. But this is a hyperbola, so I always drew a box first, and then I drew the asymptotes through that box, and coincidentally, the way I've drawn this, my other asymptote is going to look just like the x-axis. So then you draw your hyperbola approaching those asymptotes. Now, of course, this is not a computer like your textbook has to print the solutions to the odds, so you have to give me a little latitude here. All right, now, the next thing I'm going to do is see what it looks like coming out towards me. So I'm going to let x equals 6. So if x equals 6, then I get 36 minus y squared minus 9z squared equals 9. And then if I rearrange that, I get y squared plus 9z squared equals 27, right? And again, rewriting it the way we do in pre-calc, we get an equation for an ellipse. So now I'm going to draw these ellipses coming out using the y and z axis. So when x is 6, oops, I'm going to have to extend that a little bit. We get y equals square root of 27, which I forget what that's about, 5.1, I think. 1, 2, 3, 4, 5. So I'm a little off there with my hyperbola. 1, 2, 3, 4, 5 point. Yeah, I've got it going towards the asymptote a little bit too quickly. And then on the x, parallel to the x-axis, I'm sorry, the z-axis. Parallel to the z-axis is square root of 3, which is about 1.7. Oh, let's see. Oh, my tick marks, though, here should be smaller. So I'm going to make them like that. So 1.7 would be about there. So then I'm going to draw my ellipse. And then the back part is dotted because it's behind my paper. And then it's going to be symmetric, so then do something similar over here at negative 6. 1, 2, 3, 4, 5.1. That's a little better than that. 1, 2, 3, 4, 5.1. I drew it better on that side. And then coming out parallel to the x-axis again, about 1.7. Now remember, these tick marks on the x-axis being close together, that's very important, or you get all kinds of weird, funny-looking shapes. You don't have the right perspective if you don't do that. Okay, so there's my picture of my hyperboloid of 2 sheets. Now you can use your artistic talents to make it look a little nicer if you want. Putting some more curves in, like those ellipses. You can use your colored pencils. And there you have it. Okay, I want to make one more drawing of a surface, and this is a sphere, which is technically a quadratic surface, but it's a very simple one, just to show you how something round should look. So we have a sphere centered at 0, 4, 0. So we'll call that point right there. And then the radius is 4, and I set that up obviously to make it kind of simple here. So we go 4 this way, 4 that way, 4 that way, 4 that way, and that's a circular trace in the YZ plane. Now to make it three-dimensional, we're going to do a circular trace parallel to the XZ plane. So again, we're going to come out 4. Now notice it looks like I'm only coming out 2, but remember my tick marks parallel to the x-axis are going to have to be closer together than on the other axes. So there, and then back 4, so there. So that circle looks like an ellipse really, but it's a circle. It's a three-dimensional circle. And then one more to give it more 3D appearance is to do a circle like the equator. So it's going to come out like that, and then the invisible one in the back you dot. So that's kind of how you do a sphere. Number 32. Write an equation in x, y, and z for the surface obtained when 4x squared plus 9y squared equals 36 is revolved around the y-axis. So first of all, we recognize that this is an ellipse, and there it is in standard form. And there's the graph. And what we're going to use is the right side of the curve to go around the y-axis. And then I've drawn a circular cross-section on the y-axis. So here we have the equation for the curve using x1 and y1, because I'm going to preserve the actual x, y, and z for the surface. And the radius this time is always going to be x1. It's always going to be the value of x on that curve. And the circle is, x and z are varying on that circle, but y is staying the same. So the equation of the circle is x squared plus z squared equals x1 squared. And y and y1 are going to be the same. Now we're going to color code these letters, because x1 squared is equal to x squared plus z squared, so they're both red, and y1 are equal, so I've got them in blue. And we're going to take the x squared plus z squared and substitute it for x1, and we're going to take y and substitute it for y1 in that original equation. So what we get is 4 times x squared plus z squared plus 9 times y squared. And then we can simplify that, and if you like, bring the 36 to the other side. 40. Write an equation in x, y, and z for the surface obtained when z equal to x is revolved around the x-axis. So the blue line is z equal to x, and notice that y points behind the screen, because if you think about it, the y-axis was rotated back and down. And then the dotted line is the image of the line z equal to x across the x-axis, and so we've got these circular cross sections, and I've shown one on either side of the z-axis. All right, so this time we're going to use z1 and x1 for the curve and save x, y, and z for the surface. The radius this time is z1. And the equation of the circle, well, what's varying now is y and z are varying, and x is staying the same within one particular circle. So y squared plus z squared equals z1 squared. Now notice that x is always going to be the same as x1. It's not varying in that circle. And if we square both sides of our original equation, we get z1 squared equals 4x1 squared, which is what I'm going to need because my second equation has a z1 squared in it. And so I'm going to replace the z1 squared with y squared plus z squared. So that becomes y squared plus z squared equals 4x squared. The y squared plus z squared took the place of z1, and x took the place of x1. And then if you like, you can bring everything to one side of the equation. Number 46. Describe and sketch the traces on horizontal planes for the surface whose equation is z equals xy. This is not a simple quadratic surface. We're not going to draw this surface. We're just going to draw some traces. Now when z equals 1, we get xy equals 0 in the xy plane. This means that either x is 0 or y is 0. The trace is not a curve, but rather the x and y axes. So let's move on to any other z value, namely let z equal a. Then we get xy equals a, or y equals a over x, and these are equations of hyperbolas. And here's a picture. So now it's your turn to draw some pictures. Have fun, get your crayons out, and do a good job.